Electrical Measurements and Instrumentation, Lecture 7, Moving Iron Instruments. The instrument in which the moving iron is used for measuring the flow of current or voltage is known as the moving iron instrument. Basically, it works on the principle that the iron placed near the magnet attracts towards it. And the force of attraction depends on the strength of the magnetic field, and the strength of the magnetic field depends upon the current passing through the coil. The moving iron instruments or MI instruments are quite cheap in cost, simple in construction, and very accurate at fixed power supply frequency. These instruments can be used on AC as well as DC. Therefore, these are widely used in laboratories and on switching panels. These instruments are used either as ammeters or voltmeters only. Generally, these instruments are used to measure AC current or voltage, but can measure DC current or voltage also without any external circuit. Point is connected to the specially designed soft iron that moves according to the intensity of the magnetic field acting on it. The magnetic field is produced by current carrying coil. There are mainly two types in moving iron instruments. One is attraction type, which is also called as single iron type, and second one is repulsion type of moving iron instrument, which is also called as double iron type moving iron instrument. Coming to the attraction type of moving iron instrument, when a soft iron piece or vein is placed in the magnetic field of a current carrying coil, this is the coil which is in the cylindric circular shape. So the current is flowing like this. When the current is flowing like this, the iron flux is produced. When there is a flux, it having some imaginary magnet. This magnet attracts this iron piece. This imaginary magnet, whatever the magnetic lines what we have here, it will attract this iron piece. Whenever the spindle is connected to this iron piece through the pointer, because of the force of attraction, the soft iron vein is moving towards the center of the coil. Automatically, the pointer will deflect. When a soft iron piece is placed in the magnetic field of a current carrying coil, then the piece is attracted toward the center of the coil. This is because of the piece try to occupy a position of minimum reluctance. Thus, a force is exerted on the soft iron piece and a deflection in the needle takes place. A moving iron instrument consists of a stationary hollow cylindrical coil. An oval-shaped soft iron piece is mounted eccentrically to the spindle to which a pointer needle is attached. At this position, we are connected our spindle. To the spindle, we are connected our point or needle. The control in torque is provided by the gravity control method, while the damping is provided by the air friction as shown in figure. In detail, let's take as a coil. This is our coil. Wherever you measure the current or voltage, we connected these two terminals at there. Some current is flowing through this coil. When the current is flowing through this coil, an imaginary magnetic field obtained here. Because of the magnetic lines, this soft iron piece try to move in this direction due to attraction between iron and magnets. Whenever this soft iron piece moving in this direction, the pointer will deflect. If the current is more, the flux or magnetic field is more, obviously the soft iron attracts more. When it is moving in this direction, the pointer will move in this direction. Coming to the working of attraction type of moving iron instrument. When the instrument is connected in the circuit, the operating current flows to the stationary coil. A magnetic field is set up and the soft iron piece is magnetized, which is attracted towards the center of the coil. Thus, the pointer attached to the spindle is deflected over the calibrated scale. If the current in the coil is reversed, the direction of the magnetic field produced by the coil is also reversed. The magnetism produced in the soft iron piece will reverse. Hence, the direction of the deflecting torque remains unchanged because the magnetic field poles are changed from north pole to south pole when the current is reversed. But this iron piece always attracts this magnetic field. That's why even though you have changed the terminals of the coil, the direction of the pointer is unchanged. Thus, attraction type moving instruments can be used as AC as well as on DC systems. Since the deflection theta is proportional to the square of the current flowing through the coil, we will prove by deriving the torque equation later. Therefore, the scale of such an instrument is non-uniform, being crowded in the beginning. However, by choosing proper dimensions, shape and position of the soft iron piece or vein, it is possible to design and construct an instrument with a scale which is very nearly uniform over a considerable part of its length. Coming to the repulsion type of moving iron instrument. The name itself indicates that repulsion. In previously it is attraction, that's why this coil attracts this iron piece. Here some repulsion technique is used in this type of instrument. The basic principle of a repulsion type of moving iron instruments is that the repulsive forces will act when two similar magnetized iron pieces are placed near each other. We have placed two iron pieces near the current carrying coil. Whenever the current is flowing through the coil, obviously the iron pieces are magnetized with the same polarities of the two magnets. Because of that, repulsion force exists. Coming to the construction of the repulsion type of moving iron instrument, it consists of a fixed cylindrical halo coil which carries the operating current, which is our fixed cylindrical coil which carries the operating current. Inside the coil, there are two soft iron pieces placed parallelly to each other and along the axis of the coil like this. They are parallel to each other, which are isolated. One is fixed one is moving one. Because of the same polarities existing, one plate is repelled from the other plate, that's why it is moving. This point is connected to the moving iron piece. Then when this piece is moving, the pointer will move. When the intensity of the current is more, the repulsive force is more, the pointer moves more. One of the rod or vane is fixed and the other one is movable, connected to the spindle as we discussed now. And the pointer is attached to the spindle, which gives deflection on the scale. The controlling torque is provided by the springs, while damping torque is provided by air friction. Let's see the simple construction, which is our halo cylindrical coil. The current is flowing like this. When the current is flowing like this, two vanes are there. One is fixed vane, one is movable vane through the spindle. The spindle is connected to this pointer. Whenever the current flowing through this coil, these two are magnetized, and let us assume that the pole here it is north pole, the other one is south pole. Obviously it is also north pole, it is also south pole. Because of the north pole in the two vanes, a repulsion force exists, then it will move in the other direction. When the current is reversed, the polarity is also reversed. It becomes south pole, it becomes north pole, it becomes south pole, it becomes north pole. Again there is a repulsive force exists between these two. That's why it can use it for AC also. When the current is reversed, the pointer will move in only one direction. So in another way, if you see in the improved pattern, the current is flowing like this. These are the terminals. Wherever you required, we are connected these two terminals over there. The current is flowing like this. When the current is flowing like this, magnetic field is produced. Because of this magnetic field, these iron pieces are magnetized. These pieces are polarized with same magnetic field, which is north pole, which is south pole, which is north pole, which is south pole. Because of that, repulsive force exists. This one is fixed, which is moving through the spindle, so it will move. When it will move, the pointer will move on the scale. In repulsion type, there are two types of constructions. One is radial vane type, second one is coaxial vane type. In radial vane type, the construction is to be like this. In coaxial vane type, the construction is like this. But the working is same. Whenever the current flowing through this coil, these two are magnetized, having same polarities. Repulsive force exists. In coaxial vane type also, the current is flowing through this coil. These two are magnetized with same polarities. Because of the like poles, it will repel each other. Coming to the radial vane type. In this type, the vanes are radial strips of iron. These strips are placed within the coil as shown in figure. The fixed vane is attached to the coil and the movable one to the spindle of the instrument. Coming to the coaxial vane. In this type of instrument, the fixed and moving vanes are sections of coaxial cylindricals as shown in figure. The control torque is provided by the spring. Gravity control can also be used in vertical mounted instruments. The damping torque is produced by air friction as in attracted type instruments. Repulsive type moving iron instruments working. When the instrument is connected in the circuit, the current flows through the stationary or fixed coil. A magnetic field is set up along the axis of the coil. This field magnetizes both the pieces similarly, that is, both the pieces attain same polarities. A force of repulsion acts between two, therefore movable piece moves away from the fixed piece. Thus the pointer attached to the spindle deflects over the calibrated scale. If the current in the coil is reversed, the direction of the magnetic field produced by the coil is reversed. All this point is discussed through the polarity of the magnetized soft iron piece is reversed, but still they are magnetized similarly and repel each other. Hence the direction of the deflecting torque remain unchanged. Thus repulsion type moving iron instrument can be used on DC as well as AC systems. Since deflection theta is proportional to the square of the current flowing through the coil, we'll derive this part later. Therefore, the scale of the repulsion of moving an instrument is non-uniform, being crowded in the beginning, as usual in the attraction type of instrument. However, by using tongue-shaped iron pieces, the scale of such instruments can be made uniform. That is one of the advantages in repulsion. Comparison between attraction and repulsion type of instruments. In general, it may be said that attraction type instrument possesses the same advantages and are subjected to limitations described for the repulsion type. An attraction type instrument will usually have a lower inductance than the corresponding repulsion type of instrument, and voltmeters will therefore be accurate over a wide range of frequencies, and there is a greater possibility of using shunt with ammeters. On the other hand, repulsion instruments are more suitable for economical production and manufacture, and a nearly uniform scale is more easily obtained. They are therefore much more common than the attraction type. So, repulsion type of instruments more commonly used than the attraction type of instrument. General torque equation of moving iron instruments. An expression for this torque of a moving iron instrument may be derived by considering the energy relationships, where there is a small increment in current supplied to the instrument. When this happens, there will be a small deflection and some work done will be done. Let TD be the deflecting torque. Mechanical work done is equals to deflecting torque into deflection. Because of the current flowing through the coil, the pointer will deflect for certain angle. Deflecting torque into the deflection is the mechanical work done. Suppose the initial current is I in the instrument inductance is L, and the deflection is theta. If the current increases by dI, then the deflection changes by d theta and the inductance by dL. Then there is a change in current, change in deflection, change in inductance. In order to affect an increment dI in the current, there must be an increase in the applied voltage given by E is equals to change in flux linkages with respect to the time, which is EMF from Faraday's law, where psi is the flux linkages. We know that psi is equals to L into I, self-inductance into the current flowing through the coil. So which is di by dt into L into I. So I dL by dt plus L di by dt, which is voltage applied across the coil. The electrical energy supplied is, we got E is equals to I dL by dt plus L into di by dt. We know that energy is equals to voltage into current into time. So voltage into current into change in time, that is equals to I square dL plus Li di. So dt dt cancel, dt dt cancel, I square dL plus IL di. Just like this. The stored energy changes from, in inductor, the stored energy is half Li square. So, which is changing from half Li square to half L plus dL plus I plus di square, which is square. Hence, the change in stored energy is, simply subtract these two, 1 by 2 L plus dL into I plus di whole square minus half Li square. When multiplying these two, which is A plus B whole square from A square plus 2AB plus B square. Then these two are cancelled. If you multiply these two separately, these two are cancelled. Finally, we got IL dL plus half L di square plus half dLi square plus I dL square plus 1 by 2 dL di square. Neglect higher order terms in this equation. These green color highlighted ones are the higher order terms. That's why we neglect these three. Finally, we got I into L dL plus half I square dL. From the principle of conservation of energy, electrical energy supplied is equals to increase in stored energy plus mechanical work done. We already derived this mechanical work done, TD into theta. Electrical energy supplied, we already derived. Increase in stored energy is this. So, substitute all the values, I square dL plus Li di, which is derived, and which is also derived here, IL dL plus half I square dL plus mechanical work done. We know that deflecting torque into deflection. By solving this, these two are cancelled. If you take this 1 by 2 I square dl to the left hand side, you will get 1 by 2 I square dl, that is equals to TD into dt. Finally, deflecting torque TT is equals to 1 by 2 I square dl by dt, where T in Newton meter and the current flowing through the coil in amperes and inductor L in henries, theta in radians. The moving system is provided with control spring. Therefore, controlling torque is equals to some control constant into theta, where k is the control constant in Newton meter per radian and theta is the deflection in radians. At equilibrium or final steady position, controlling torque is equals to deflecting torque. So k theta is equals to half I square dl. Therefore, deflection theta is equals to 1 by 2 I square by k dl by dt. Hence, deflection theta is proportional to square of the RMS value of the operating current. The deflecting torque is therefore unidirectional, whatever may be the polarity of the current. Whenever you are squaring this current, you will get the positive one only. That's why the deflecting torque is unidirectional only in moving iron type of instrument. Coming to the advantages of the moving iron instrument. The moving iron instrument is independent of the direction of current and hence use it for both AC and DC systems. The moving iron instrument requires less number of turns as compared to the PMMC instrument, thus it is cheaper. The moving iron instruments are robust and simple in construction. These instruments are reasonably accurate. The moving iron instruments possesses high operating torque. These instruments can withstand overloads momentarily. The friction error is very less in moving iron instruments because their torque to weight ratio is high. The torque weight ratio is high because their current carrying parts in stationary and the moving parts are lighter in weight. These advantages of moving iron instrument. The scale of moving iron instrument is non-uniform, crowded at the beginning. Therefore, accurate readings are not possible at this end. These instruments are not very sensitive. Some serious errors occurs in the instrument because of the hysteresis, frequency and stray magnetic field. Power consumption is quite high in the moving iron type of instruments. Errors are introduced due to change in frequency in case of AC measurements. Coming to the errors in moving iron instruments. There are two types of errors which occurs in moving iron instruments. One is errors with both AC and DC. Errors with AC only. Let's discuss about errors with both AC and DC. In that, errors due to hysteresis. Because of the hysteresis in the iron parts of the operating system, the readings are higher for descending values but lower for ascending values. Hysteresis means whenever you apply AC supply, the current is alternating current. So when the current is alternating, so magnetization, demagnetization takes place in the coil. Because of that, one loss is produced in the core. That loss is called as hysteresis loss. Because of the hysteresis in the iron parts, the readings are higher for descending values but lower at ascending values. That is one of the error. The second one is the hysteresis error is considerably reduced by using mu metal or permalloy which have negligibly hysteresis losses. We can use these metals for reducing these errors. Coming to the second one, errors due to stray magnetic fields. Since the operating magnetic field of the moving iron instrument is comparatively weak, therefore stray fields, which means fields other than the operating magnetic field, affect these instruments considerably. Thus the stray fields causes serious errors. These errors can be minimized by using an iron case or a thin iron sheet over the working parts. Coming to the third one, errors due to temperature. The effect of temperature change on moving an instrument arises mainly from the temperature coefficient of spring. With a change in temperature, stiffness of the spring varies, which occurs error. However, for voltmeters, both the temperature coefficient of spring and the temperature coefficient of resistance of voltmeter circuit may balance each other. Errors in AC only. Error in moving an instrument due to change in frequency. The change in frequency produces a change in impedance of the coil and change in magnitude of eddy currents. The increase in impedance of the coil with the increase in frequency causes serious errors in case of voltmeters only. However, these errors can be eliminated by connecting a condenser of suitable value in parallel with the swamp resistor R of the instrument. The impedance of the whole circuit of the instrument becomes independent of the frequency if C is equal to L by R square, where C is the capacitance of the condenser. Coming to the ranges, ammeter from about 0 to 20 milliamperes to 0 to 800 amperes maximum without the current transfer. Above this range, we need to use current transfer for the extension of range of ammeter. In voltmeters, from above 0 to 1 volt to 0 to 800 volts maximum without the potentiometer. If you want to extend other than 800 volts, we need to use potential type of instrument. A moving iron instrument can be used for AC or DC, but they are mainly used for AC measurements via AC currents and voltages. They also can measure DC quantities, but their characteristics are inferior to that of permanent magnet coil instruments. Therefore, in DC measurements, permanent magnet moving coil instruments are preferred and used. Thank you.